All right, so this video is going to be on the SN1 mechanism. So remember, this is substitution, nucleophilic, unimolecular. Okay, so really what this boils down to is how many species are present in the transition state. So, or the rate determining step. So we've got this bromine as our leaving group. We got the acetate labeled in red as our nucleophile. And then we've got them on the right side, right? But so this is clearly a substitution reaction. But since it's an SN1 reaction or mechanism, that means that the rate is equal to K times the concentration of only the alkyl bromide. In this case, the nucleophile concentration is not relevant in the rate of this particular reaction. And so here's the first step. Bromide leaves, forming that carbocation intermediate, at which point the nucleophile then attacks. But since this is a two-step mechanism, we do have a rate determining step, and that is the first step. That is the slow step. And so that's why the concentration of the alkyl bromide is the only thing that matters in this case. And so just to point it out, this is our carbocation intermediate that we might see at that trough of the energy diagram. Okay, so let's take a look-see at that energy diagram. We got energy on the y-axis and reaction coordinate on the x, right? So here we go. Two humps is a two-step mechanism, and that is an SN1 energy diagram right here. So we have the transition state right here for the first step. And that is a partial bond breakage of that carbon-bromine bond, and so we have a delta positive for the carbon and a delta negative for the bromine, and carbocation intermediate there for you. Okay, so that is essentially when we would, in theory, have the acetate be present and actually make a difference. And so that does have its own transition state where we would have partial bond formation of the acetate when it attacks that carbocation intermediate. So that the carbon has the delta positive, and the oxygen has the delta negative in that case. And then we end up getting our desired product. Okay, that substitution product. So there's a lot to draw, so bear with me. I'm trying to use these beautiful dotted lines here. So we want to make sure that we're able to identify the activation energy as well as the enthalpy. So here's the first activation energy EA1. There's delta H1, and then we have EA2 here, and then we've also got delta H2, which we need another line right here. Boom. Okay, so there's delta H2, and then right here on the far right, we actually have delta H overall for the overall reaction. So that does show that we have an exothermic overall reaction. Okay. Now, just like the video for SN2, we want to talk about the stereochemistry of the SN1 reaction. So remember, SN2 resulted in an inversion of stereochemistry. But for stereochemistry of SN1 reaction, it's a little bit different because we have this carbocation intermediate that is sp2 hybridized. And so what that means is that it is trigonal planar. Okay, so since it's flat, that makes a huge difference on the approach of the nucleophile. So the nucleophile can technically approach from the top or the bottom, or if you want to think about it in terms of like the SN2 verbiage, we had front side attack as well as back side attack, right? And so since it's planar, though, again, the steric hindrance is kind of not relevant here, and it's the approach from the front or the back is equivalent. Okay, so they're equally likely in this case. So how does that affect the stereochemistry of the products, you ask? Well, let me just tell you, and let me show you real quick. All right, so we've got this chiral substance right here. Now, if we had the first step 1, that bromide leaves, right? And so what we end up getting is a carbocation intermediate shown here. Now, this is again a planar carbocation, so that means the nucleophile can attack from the front or the back or the top or the bottom, depends on how you want to look at your carbocation. So what that means is that if we have front side attack, or if you want to think of it, the top, that would be like attacking from outside of the computer screen. We would have the methyl forced back and the nucleophile projected out towards us. That would actually be inversion of stereochemistry, like we saw in SN2. And then if we had backside attack in this case, we would have attack from the bottom. Again, this is all just dependent on how we're looking at the carbocation, because the carbocation is planar, so top or bottom, front or back, doesn't matter. Whereas when we're talking about the SN2 reaction, it's backside attack, because we're talking about the nucleophile attacking with respect to the location of the leaving group. Okay, so I don't want you to get confused in that sense when we say front and backside attack for SN1 versus SN2. Okay, so I do want to mention that bottom reaction is going to be a retention of stereochemistry, because the nucleophile replaced the bromine, i.e. the leaving group, and it has the same stereochemistry with respect to all the rest of the groups. Okay, so now if we look at the left side, if that's a pure enantiomer, then that means that we end up getting a mixture. And what that is called is racemization. So we get a 50-50 mixture of two enantiomers from a pure enantiomer. And again, that's just another way to say it forms a racemic mixture. Okay? And so that's one of the characteristics of SN1 reactions, is that racemization does occur. Okay, so let's look at some examples of practice, basically just some quick ways to kind of jump to the products. So remember, we end up doing, for SN1 reactions, we want to have retention of stereochemistry as well as inversion of stereochemistry. So if this is an SN1, we have to make sure that we know iodine is our leaving group. I'm going to highlight that in blue. Red is going to be our nucleophile, which is water. Now, two products are possible. We have, again, the iodine can just leave, and we can replace that with the OH group that the water provides in this case. And so that would be the reaction on the left. That's retention of stereochemistry, and then our compound on the left, and then the compound on the right is our inversion of stereochemistry. And remember, these two products are all possible because of that carbocation intermediate formed after the iodide leaves for SN1 mechanisms. So let's try this problem now. We have this, remember, our chlorine is going to be our leaving group, water is going to be our nucleophile. We are indicating this is an SN1 reaction. Now what that tells us is that we're going to have a 50-50 mixture of two different enantiomers, right? And so what I'm going to do is just basically copy and paste this particular, almost like a skeletal structure of the compound, and instead of and then replace the nucleophile, or replace the chlorine, rather, the leaving group, with the nucleophile. Okay, and so that, let me highlight this in blue real quick just to keep consistent. That is going to be red. Now on the right side, if we replace that chlorine with the nucleophile and keep it as a wedge, that's just retention of stereochemistry. If we make it a dash, that would be inversion of stereochemistry. Again, 50-50 mixture of both. Okay, and so these are both racemic mixtures. Again, that is 50-50 mixture of S and R configuration, or enantiomers. And again, a characteristic of an SN1 reaction. Really trying to hammer it in there, okay? So make sure we're aware of this. SN2, inversion of stereochemistry from backside attack of that nucleophile. SN1, since we have that planar carbocation intermediate, we just get 50-50 mixture of enantiomers or compounds in the products. Okay, so, and of course that's only if we have a chiral center, right? So we're not going to notice the inversion or retention of stereochemistry if it's not a chiral center. Okay, so moving on, identity of the R group does matter in this case in terms of the effectiveness of an SN1 reaction. So if we have a methyl with a leaving group, then we have a primary, secondary, and tertiary carbon with leaving groups on there. Remember, oops, come on now. My iPad's silly. Just trying to make me do weird arrows. I want to do this crazy arrow like this. I just like the way it looks. Maybe you guys don't, but I love it. Just draw an arrow with a little bit of text inside. So now, what we have here is, as we go from right to left, we have a decrease in the number of R groups, and we also will have a decrease in the rate of the reaction for SN1 reactions. Okay, I drew it from right to left because that's what we had for SN1 reaction. Okay, so I want to make sure that we highlight that point. It's a decrease from right to left, whereas an SN2 reaction was an increase of the rate from right to left. So what that means is the tertiary is super fast in this case, secondary is going to be slower, and then primary and methyls are actually just not going to occur for SN1 reactions. Okay, and that's because primary carbocations and methyl carbocations are not happy. Okay, so I wanted to summarize everything for you, just as we did for SN2, but now I'm combining the two. So we have our SN2 reaction with the kinetics, mechanism, stereochemistry, and identity of R group. We've already seen this before, so we got the second order with the rate dependent on the concentration of the alkyl halide and the nucleophile. We have a one-step reaction with backside attack and inversion of stereochemistry as a result. And the identity of the R group is, if we have, it matters, and it affects the rates if we have unhindered our carbon center that is kind of involved in that reaction, then it's going to be a faster reaction. So for SN1 reactions, it's first order now because the rate is only dependent on the concentration of the alkyl halide, which makes it a two-step process. And since we have that trigonal planar carbocation intermediate, we will get a racemization of the products. Okay, so we're going to get inversion of stereochemistry as well as retention of stereochemistry. And then the identity of the R group, it matters again because of more substituted, we get a faster reaction rate. Okay, so let me know if you have any questions. Bye.